Okay, hello everyone. Welcome to this session. First talk is by Jack Liell-Cock on an earlier announcement of compositional imprecise probability.
Thanks for coming, everyone. So yeah, I'll be talking about compositional imprecise probability today. So this is joint work between myself and Sam Staton. So it's an early announcement, so we won't be in the proceedings, but we do now have a preprint up online if you want to have some extra reading about this after the talk, or just feel free to come chat to us as well. So to give a brief overview of this work, basically what we're trying to do here is give a fully compositional account of Bernoulli uncertainty with Knightian uncertainty. So Bernoulli uncertainty is the type of uncertainty you get when you flip a coin with known bias, and it could be heads or tails, but you just don't know what the outcome is because it's probabilistic, but you know at least what the distribution is. Knightian uncertainty, on the other hand, is where you know that you have a biased coin, but you have no idea what the distribution of the biased coin is. So someone gives you a biased coin, you flip it, you know it's biased, but you don't know, you have no idea what the bias could be. So this is usually modeled with non-determinism. So we just have a set of possible outcomes that could happen, but we have no weighting on what these outcomes or the likelihood of these outcomes occur. So we basically give a compositional account of these two uncertainties together using a graded perspective and named Knightian choices. And we show two things about this account. Basically, it gives a refined bound on uncertainty when we have two programs which use these two types of uncertainty and we compose them together, we actually get a refined bounds of what the Knightian uncertainty of the overall program would be. So it's tighter bounds. And also it's maximal among all other compositional accounts. So there's no way we can quotient our theory or language any further without basically breaking something in either the imprecise probability sense or in the compositional sense. So just to give a brief overview on other work, which is related, but not quite this work. So there's a much broader interest in combining non-determinism and probability. So say, I guess, probabilistic databases and all that. But in this work, we're primarily focused on the imprecise probability case. So compositional language, which can support imprecise probability. Okay, so this is, To start with, what is imprecise probability? Well, probability is just, we can represent probability as given a set of outcomes. We have a simplex with each outcome at a point, and we can represent the probability as a point within this simplex. So we can take this first point here, it's in this top left triangle. The point which is right on the outcome red would be a point which represents the distribution that we have 100% chance of having red as an outcome and 0% chance of having anything else. This point Q in the middle here basically represents, because it's in the center of mass of the whole triangle, represents equal chance of getting each of the three outcomes it's equal chance of each of the three outcomes occurring. And our final point P here, which is equidistant between green and blue, would represent 50% chance of green occurring, 50% chance of blue occurring, but impossibility of red. So if we think about probability in terms of, I guess, the Bayesian interpretation, so basically it's the fair bet you would get given a probabilistic view of the world. What imprecise probability says is some of these probabilities, we don't know what the actual distributions of some of our data is. And all we know is that possible cases can occur, but we don't know, how to weight these possible cases. So this generalizes our analogy to be convex sets of points. So say in this example on the top right here, we have say we have one worldview, which basically says that if this happens, then there's a 50% chance of green occurring and 50% chance of blue occurring. And another worldview, which says if this happens, then there's a 100% chance of red occurring. And say we have some Knightian uncertainty about which of these two worldviews we have. Well, so some distribution that we don't know uncertainty, which we don't know what the distribution is. Well, that basically gives a worldview where it could be any one of these possible outcomes. So the distribution could be any one of these possible outcomes as a convex combination between our two outcomes. So we represent these things. And the reason we have convex sets of points is because if we have one possible, so if we think of probability as a fair bet, and we're willing to take bet A and willing to take bet B, then we should be willing to take any convex combination of these two bets. So basically, in order to build a first language with support for imprecise probability, which is both Knightian uncertainty and probabilistic uncertainty, we want to build a first order language without recursion. So basically, what we want in this language is if then else statements to operate on our Booleans and our probabilistic Booleans. We want sequencing with a mutable variable assignment, and we want two different commands. The first command is a command Bernoulli, where we can think of that as a fair Bernoulli trial. So we're given a coin with heads up with true on one side and false on the other, and it's got a 50% chance of either one occurring. And when we call this Bernoulli command, we flip the coin and we get a Boolean value. Now we have another command called knight, and this is basically a Knightian choice. So we can think of this command as basically someone giving us a coin. They say it's a biased coin, but we have no idea what the bias is. So when we flip this coin, we're basically kind of getting when we flip this coin, all possible outcomes of basically all possible distributions could occur where this coin could either be 100% returning true all the time or 100% chance returning false all the time. So those are two of the extreme values and any possible distribution in between. So that's how we represent that as a convex set there. And usually we talk about this as just the two extreme values of the convex set because they're equivalent to each other. So how can we actually build these convex sets by using these programming constructs and these programming constructs in our language? Well, we can look at this first example here where we don't have any Knightian uncertainty. And all we're doing is taking a fair Bernoulli trial, conditioning on that and returning green if it's true and blue if it's false. And so here we basically get the single point halfway between green and blue, because that's to say, 50% chance that this program will turn the result green and 50% chance that this program will return the result blue. On the other hand, if we add a little bit of complexity and bring a bit of Knightian uncertainty into our program, then what we say here is that, and we use this logic to combine it, well, what the Knightian uncertainty is saying, okay, so Z is a fair Bernoulli trial, but X could either be, say, in one extreme, the coin which always returns true. And if this is the case, basically this program will always return red because it doesn't matter which Bernoulli branch we go down, will always return red when X is true. Or on the other extreme, this could be, X could be the distribution which always returns false. And so in this case, the program will have 50% chance of returning green or 50% chance of returning blue. And basically because X is any possible base distribution between these two extremes, we get the convex combination between 100% chance of red and 100% chance of green. Now, if we increase the complexity slightly more and have two Knightian, basically we draw from two Knightian choices or have two Knightian uncertainties. Well, now, and so the only difference between this program and the first program is we condition on Y in the else statement of the Bernoulli trial. Then here, basically, since we've decoupled the Knightian uncertainty, we could have, say, X being the distribution, which always returns true, and Y being the distribution, which always returns true. And so that will always return red, as we saw in the first program. But we also get additional types of combinations where, say, X is the program, which also always returns true, and Y is the distribution that always returns false. And there we'll get 50% chance of red happening and 50% chance of blue happening. And we can take each of those 4 points of true, 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 false, false, true, and true, false, and these will give us the 4 extremes of this square here. And because our distributions can be any kind of combination, well, these distributions can be any kind of combination of these 4 extreme, distributions, then we get this full complete square as what the convex set that this program represents. Okay, so what kind of desirabilities do we actually want from our programming language? Well, first of all, we want our programming language to be commutative. So given 2 variable bindings, say X from program T and Y from program U, if they don't depend on each other, so that's X doesn't appear anywhere in U and Y doesn't appear anywhere in T, then we should be able to swap these bindings around because they're independent. And additionally, we want our program to be affine. So if we bind X from a program T and continue with U, but U doesn't reference X anywhere in its program, then that should be the same as just simply dropping the original binding because we're not using it later in the program. So the reason we want this type of desiderata is because basically this allows us to model our program as data flow diagrams. So we can see this middle program here, which runs program U and T, and this other program here, which runs program T and U. Well, there's no ambiguity about writing both of these programs like this because they'll always be equal. So we can just represent our entire program as a data flow diagram. And we can also interpret our programs in Markov categories, which we'll get to later. So the second desirability that we want within our program, within our programming language, is basically standard equational reasoning about if then else statements. So basically, in particular, we want this hoisting equation here. So if we bind X from a program T in both of our if branches, basically, this should be the same as hoisting that binding out, provided that X is not free in B, and then just binding it before running our if conditional. Okay, so what kind of problems do we run into when we actually try and satisfy these desiredata? Well, the most common method in order to actually handle both Bernoulli uncertainty and Knightian uncertainty is this convex power set monad. And I won't go into the details here because inevitably it won't work for our case. But what the convex power set monad does is basically, given a set of possible outcomes, it gives the set of convex distributions of all possible, the convex set of distributions of all possible outcomes, or finitely generated distributions. So given this set, it will return, this is one possible outcome of the monad, this is another possible instance of the monad, and also individual points because they're all convex sets. But the main point is we can interpret these two commands, Bernoulli and Knight, in a programming language by modeling a programming language with this monad. But the issue is that it's no longer commutative. So basically we have this program down here, which just takes two Booleans and does some logic on them. And we can see that if we run the Knightian choice first and pass it into Y, and then Bernoulli choice and pass it into X, and interpret that with the convex power set monad, that will actually give a different convex power. This will give a different convex set to the one if we run the Bernoulli command first and the Knightian command second. So yeah, we don't have a fully compositional account via this monad. And it turns out any semantic model that satisfies our desiredata cannot actually distinguish the two following convex sets, among other sets that can't be distinguished. And the main issue is basically for these two sets, this program here, where the paradox kind of comes up where in each of our if branches, we're creating new Knightian uncertainty and binding them to the same variable X. And the question arises is, are these the same Knightian uncertainty, or do we decouple the Knightian uncertainties, or do these come from the same kind of Knightian seed, or do these come from different ones? And it turns out any language which satisfies our desiredata cannot distinguish these two kind of cases here. So in order to solve this problem, the simple solution is to make this explicit. We're explicitly saying which Knightian choices are related to each other. So basically, what we're doing to our programming language here is saying each Knightian choice is given a name, and this name kind of represents the seed of the Knightian distribution that is bound to this variable. So this first program is the exact same as the one we saw earlier and aligns with this convex set here, where we're just conditioning on a Knightian and a Bernoulli. But this is equivalent to this program because even though we use a different variable y here, because we're pulling it from the same Knightian seed, because we're using the same because we're using it the same. The name represents the same Knightian seed, and so this will actually return the same result. We're saying these two things, these two Knightian uncertainties are actually coupled together and will always produce the same results. However, this is different to the last program, which represents the convex set on the right, because what's happening here is we have two different Knightian uncertainties. We have two different seeds. So now we're saying these Knightian uncertainties are decoupled, so we can possibly have the case, say, where X is the distribution which always returns true, and Y is the distribution which always returns false. And so this program can return the outcome, which is 50% red and 50% blue. So it creates this point here, which was impossible with the first two programs because these two Knightian uncertainties were coupled together. Okay, so in order to actually create a monad which supports these two types of uncertainties, what we do is we create a reader monad transformer of the finite distributions monad. So what's happening here is Knightian choices or non-determinism is given by reading our names from these Knightian choices to A. So the Knightian choice is A, so the A represents the Knightian names, and basically each A corresponds to this distributive coin flip. And then, so if we read a specific point, if we read from one of these coin flips, then we get a distribution on our outcomes. And so each of these readings gives a different distribution. So each of them give a different non-deterministic branch. Of course, Bernoulli choices are given by the distributions. So we represent them just by the distributions monad, which is finite distributions, which is this monad here, D. And then we actually end up going a step further and generalize the Knightian choices to A just to arbitrary sets B. So we can think of these sets B as basically all possible non-deterministic branches that our program could take. So given one point in the set B, if we pass this
point B into our function here, it'll give us the distribution we'll get at the end, given this non-deterministic branch that we have chosen. So each of these points B represents a different non-deterministic branch, or a maximal non-deterministic branch within our program. So then we can actually recover the convex power set associated with each of these terms by pushing forward the maximal convex distribution on B. So we take basically the convex distribution, which covers all of B. So all possible distributions we could have on B. We use the Kleisli bind of the distributions monad to push forward over this function here, and then we get a convex power set within our output values, or our possible values. So given this monad construction, or given this monad, we want to construct a category to actually interpret our programming language. We want to construct a category where we can actually interpret our programming language, which turns out to be a graded category because we grade these, we end up grading the monad by these Knightian names. So just to give a little bit of background, a Markov category is a symmetric monoidal category such that every object has a commutative comonad structure. So basically, for each object, we have this copy map and this delete map, and these satisfy some equations. A distributive Markov category is basically a Markov category with extra structure. So it has coproducts such that, we have specific equations hold, and then the coproduct injections actually commute with the copy maps. The coproduct injections are deterministic. Okay, so one example of a Markov category is Finstock, which we'll be using in our construction here. So Finstock is the distributive Markov category where the objects are natural numbers and the morphisms between them are stochastic matrices. So for each object, for each function n to m, we have a stochastic matrix with m columns and n rows, I think, or the other way around. And each of these columns sum up to 1. We also need this category Finstock surge, which is basically a subcategory of Finstock, which has the same objects, but we only look at surjective stochastic matrices. So these are functions where when we lift, so we can think of Finstock as basically the Kleisli category of the distributions monad. And then when we lift each of these are the functions where when we lift them using the Kleisli lifting, they become surjective functions in Finstock surge. And finally, we get to the category we're going to use to actually interpret our language, and that is imp. So imp is the category of is the Finstock surge graded category of Finstock. So the reason we need surjective functions here is to actually handle the non-deterministic branches the right way, because it keeps the connection between convex power sets, which I won't go into the details here. But what we can think of this any morphism in our category here from x to y. Graded at A, or x to y gives us all the probabilistic. The x to y gives us the probabilistic morphism. So the Bernoulli, it gives us the Bernoulli uncertainty, and the grading at A represents each value at A, because A is a natural number, tells us how many non-deterministic paths we could take in our program. So basically each morphism in imp x to y graded at A, we give it as a morphism as we tensor A by x, and these are all morphisms here. And so that's how, this category actually supports finite probability and finite non-determinism. So the way we can implement Bernoulli or interpret Bernoulli in this category is it's just it's the morphism going from 1 to 2, and we grade it at 1 because Bernoulli doesn't create any non-deterministic paths. It's fully it's the distribution is fully known. And so this is just the column vector, which gives us 50% chance of, true, or the top output, and 50% chance of false, or the bottom output. Knight, on the other hand, is another morphism in imp, but now it's graded at 2, because with Knight, we basically have either the chance that there's 100% chance that, the distribution, it will always return a value of true, or the distribution will always return the value of false. So these are the two maximal, branches we could take. And then, because we can represent the convex combination of, we can basically correspond the convex combination of these, or the convex set, as just the maximal points. We give this as the unit diagonal of 100% true, or always returning true, or always returning false. So in the first branch, will always return true, and then the second branch will always return false. And then the convex combination of these two branches gives us the full 90 gives us the full set of 90 possible distributions of our coins. So yeah, composition in this category we uses basically independent non-deterministic branches. So when we compose two functions together, we basically say that these are two non-deterministic, so these two sets of non-deterministic branches that could happen in each program, so one being set A and one being set B, we tensor them together to say, and that basically says that each program uses completely independent non-deterministic choices. So for each non-deterministic choice in each program, we have a new non-deterministic choice in the final program. And this category has a monoidal structure too, where basically if we juxtapose two programs together, we also use independent non-deterministic branches in the resulting program. Okay, so what have we actually shown? What can we actually show about this program? Oh, sorry, what can we actually show about this model or this language? So basically, what we have is there is a mapping from any morphism in our category imp to a morphism in the Kleisli category of the convex power set monad. And the way that happens is for each point at X, we'll have a column vector, which represents each of the possible non-deterministic branches we could take. So each column vector is the possible non-deterministic branches, and then and the values of these column vectors represent basically the deterministic output of the program. So the first one will only return red, and the second one will only return 50% chance green, 50% chance blue. And so we can map each of these points to a point in our simplicial set and take the convex closure of them, because we're looking at all possible deterministic choices between these two extremal values. And that gives us, yes, this convex set of distributions, this gives us this convex set of distributions that the morphism in corresponds to. So what we can show is this mapping actually generates an Black's functor. So given any two morphisms, if we combine them in imp, and then we take the mapping across to the Kleisli category of the convex power set monad, we actually get a subset of what we would get if we mapped each morphism individually and then compose them in the Kleisli category of the convex power sets. So basically, this subset here is basically a subset of the convex sets. So basically, if we have a smaller convex set, we have less 90 in uncertainty. So we actually have refined bounds in our composition in the end. And finally, we have a maximality theorem. So basically, this theorem says that, our language gives rise to a compositional theory of equality. Our language gives rise to a compositional theory of equality, and we show that this theory is actually maximal in the sense that we can't equate any two free terms within any two free programs we can't equate any two free programs without either breaking basically the connection to imprecise probability. So if we equate two free terms, we'll basically equate two convex power sets, which shouldn't be equated in terms when we give the interpretation in imprecise probability, or we'll basically break the compositional structure. So something will break, whether it's, I guess, the commutivity of the monad or another part of this compositional structure in the month category. So in conclusion, what we've done in this work is basically we've taken a graded perspective and named our Knightian choices, and that has allowed us to give a fully compositional account of Bernoulli uncertainty along with Knightian uncertainty. So first of all, we have shown that when we compose programs within this account, we basically get a refined bounds on the uncertainty. We're guaranteed to have a Knightian uncertainty, which is less than what we would have done if we were using the convex power sets method. And also we show that there's no better we can do than this account if we want to either maintain if we want to both maintain our connection to imprecise probability and convex sets, as well as if we want to maintain our compositional account. So for future work, we want to look into bringing iteration and potentially infinite dimensional structures into our programming language. So some things break to do with the convex power sets there that we want to fix. We also want to make our language higher order, so implement function spaces potentially via QBS. And of course, we want an actual implementation of our language which can do inference with both Bernoulli uncertainty and Knightian uncertainty. So thank you.
thanks. That was a good talk. So you had, I mean, you talked about how the convex browser monad
Is not commutative. Yeah.
and then you had this other monad, which is a reader-like thing where you were mapping it to distribution. I didn't quite understand what the relation between that monad and the graded category imp that you eventually described.
Okay, so yeah, I guess that follows from a result from the paper that I didn't want to go into too much detail here, but basically, if you have a graded, commutative, relative, strong monad on set, that actually is equivalent to a graded distributive Markov category. So we have that correspondence in the paper, and basically, so this monad here, we actually show, yeah, we can make it a graded monad based by grading it with respect to B. So the set of non-deterministic paths, and then yeah, we pull that across the correspondence, and then that gives us this this graded Markov category, which we can actually interpret the morphisms in. Does that make sense?
Yeah.
He was Knight. I actually don't know. Do you know who Knight was? He was a guy who's in I think he was in
Determinism. Now I realize that.
yeah. I think he was a guy in economics, was he? Yeah. So he was a guy who like basically said, I don't know if he's the one who said like, yeah, you don't need to worry about your error bounds, but your error bounds on your error bounds. But he's the one who is worried. He was worried about basically like, yeah, I think black swan are kind of events in like economics where you just can't even tell when these events will occur. You just know that these possible branches are happening. And so he kind of coined this term here. And yeah, that's sweet. I think it's a very common phrase in like infrabasionism and AI safety kind of things, which is, yeah, where we stole this term from.
Why should I think of a uncertainty on my probabilities as a complex distribution, not like a trial and trials? And why is it not a distribution?
Why is it not a distribution?
Why is it complex?
Sorry, how do you mean? As in like, so basically,
It's like a distribution.
as a distribution. So, well, sometimes you don't know what the distribution is, right? Like you have just a set of certain outcomes that you know are possible, but you don't know. You have no idea as to how that even like maybe you can't even put a measure on like the set of like outcomes that could occur, and so you just can't put a probability distribution on, I guess, these distributions. So what the convex set is basically saying is saying, okay, we just look at all possible paths that or all possible, I guess, branches that could happen within our all possible branches that could happen like within our all possible branches which could happen within our model, and we just include all of them because we can't, weight them in any way.
If you take the other approach of defining distributional distributions, then this would allow to the uniform distributions on those convections. Probably also be created like that.
Then if you have a distribution on your distributions, this would amount, where does the uniform, oh, sorry, you have a uniform distribution. Yeah, sorry.
Because everything in this convex subset, like,
Yeah, so, but again, so that like breaks down, say, if you maybe have like infinite time horizon type of events and stuff, how do you put a uniform distribution on infinity? Or there's a bunch of other situations where you just can't even like put, you can't even put a measure on kind of the distributions you want to use. So you have no hope of even like defining a uniform distribution if you don't have a measure on your space.
What about, like, could you, how much does the kind of shape?
Could you use more general shapes? Well, we want, so basically this is basically, there's a result in the imprecise probability literature, which basically says, each of these kind of like, basically so a provision is basic in imprecise probability is similar to like an expectation in regular probability. And each of these kind of like provisions or worldviews is in one-to-one correspondence with these convex sets. So basically, like the convex sets in imprecise probability kind of represent all possible these are kind of like all possible kind of like, I guess, worldviews or worldviews you could have. And I think generalizing them to like non-convex sets is possible, or is potentially possible, but I think you break a lot of the connection between like, I guess, yeah, the maths and what's happening in the real world.
Or the with the constraints, you're gonna have to.
So thank you, speaker again.